Okay, so we have a function y equals sine inverse of x, and we also have y equals something. I left it blank for a reason. And we are going to revolve it about the y-axis. As I mentioned in class before, what is the first thing to do? For starters, we are going to graph so y equals second sine, you get sine inverse. And now I'm just going to graph with, okay, what should we do next? We're getting a funky graph. Certainly, we have to adjust the window. So let's go from 0 to 1. And let's do -2 to 2. See what happens. So 0 to 1 is not helping. -2 to 2 seems to help. So adjust it a bit more. You can do zoom 0, whatever. I'll leave that up to you. So I'll do -5 to 5. And over here, -5 to 5. I get that. You look at it and like, what the hell is this? Why am I getting a weird graph that's ending in that manner? You should know the answer as to why the graph looks like the way it does. So again, I left one of the y's as blank for a reason. So domain, range, let's say y equals sine x. The other one, y equals sine inverse of x. The domain of sine x is from -infinity all the way up to +infinity. The range, on the other hand, is from -1 to 1. What happens when you do an inverse? What happens to the domain and range when you find a function's inverse? They switch. Very good. Range becomes domain, domain becomes range. So this goes up there, and that comes over here. So this is fine, -1 to 1. And that's exactly what our graph is showing us. The y value goes from -1 up to +1. Great. So I don't need to go all the way up to -5. Why not stop at 2? Okay. What about the domain? The domain is technically, it has to be -infinity to +infinity, but that's not correct. Why? The calculator is not doing it. y. Gave me the correct answer that the domain and range should switch. I completely agree. That's what we're supposed to do. We did it, but this one is not right. The range. Very good, Caleb, because they wouldn't be functions, will fail the vertical line test. So what do we mean by that? Well, we know a sine function goes this way and poorly drawn sine function. And if you flip it and you say, well, I want to find the inverse, technically, not exact, something like that. That's what I would expect to get. But that is not a function. We cannot do that. So what the calculator does, stops right there, and that is what you see there. Okay, now that we have an idea about the curve, we're not fully there. So we have established, well, x values, they're going to go from -1 to 1 for reasons that we discussed earlier. I would like to know what the y values are. In other words, the y value that corresponds to that point and that point. Thoughts? Sine pi over 2 is 1, sine negative pi over 2, -1. So we're going to have pi over 2 as the lower endpoint, negative pi over 2, and positive pi over 2, upper endpoint. Worst case scenario, if you still can't figure it out, use your calculator, trace, move that arrow up. It's not helping a lot, but 1.278. Well, what is the closest number in terms of pi? Well, there are plenty, but based on our unit circle, well, it is pi over 2. 3.14 divided by 2, 1.57. So that point's probably pi over 2. Well, similar manner, you go to the negative side, it will be negative pi over 2. So by all means, this is incorrect. Negative pi over 2 to pi over 2. Reason being, we need a function. In other words, it has to satisfy vertical line test. That said, I can put a couple of restrictions in this, but where should a reasonable point be for us to stop the disk? If you have to take a guess, I'll give you this. Y has to be greater than or equal to 0. My question to you is, what should go here based on the picture that we have? Bryce, any thoughts? So back to the calculator. My question is, what should that upper point be? pi over 4. Why? I'm curious. So if I trace again, pi over 4 is 1.57. Divide that by 2 again, so you have 0.707, not 0.707, 0.75 something. So trace back somewhere right there. So nothing wrong. I could opt for pi over 4, but my question is, what is the maximum value where my disk should stop? So your current answer puts me at the point approximately where you see the cursor. Clearly, that is not the maximum point where the strip could reach. Change your guess. 1. Why 1? It's definitely way off. Bryce's answer is close. But look at the cursor. If I put a strip, it is not stopping at the maximum value. So I want to go all the way. Very good, Jaden. The highest y value is pi over 2. So the maximum point that I can get to is pi over 2. So that is my restriction. So y equals pi over 2, y equals sine inverse of x. I also put y greater than or equal to 0. Okay. So I can simply draw that picture here. I know these days there are apps and stuff, but I'm old style. And I personally believe that when you draw stuff, you learn better, even if you're not a great artist. So something like that. So my line up there, oops. Oh, the struggle is real. Okay, so that is my line. So y equals pi over 2. I put another restriction. The restriction is y greater than or equal to 0. In other words, only the positive side of my function along the y-axis. And I am going to revolve about the y-axis. So first question, where should I place my strip? The strip is going to tell me where the disk is going to be. So should it be vertical? Should it be horizontal? So we are revolving about the y-axis. So if I put the strip horizontally, then the strip is going to move along the y-axis, which is going to help us generate the volume. Well, let's see if I can draw this. Something like that. For now, it's just an approximation, which will tell us that when I spin, what is the solid I'm going to get. That is the shape of the solid I'm looking at from sideways. 0, I find the upper limit. Upper limit is pi over 2. Thickness, dy. Oh, sorry. dy. So that is the thickness of the disk, and that disk you're going to integrate it over. So we know volume is integral area multiplied by thickness, in this case dy. It is a circular disk. A circular disk, when it's infinitely thin, is simply a circle. So a circle's area is pi, and we want to find its radius. So, well, what is the radius? What should go here? That's what I'm asking. The radius of this strip it's going to be some arbitrary x. So if I move this strip up and down, so first time I drew x, I'll call it x1, put it in another position, moving the strip up, I get another x position. So as I move the strip up and down, in other words, I move the disk from 0 all the way up to pi over 2. X values are changing. X is going to tell me the radius of the disk. So here we will have x squared. Well, I've got x squared. I know the limits as to where you should start and where you should end to find the volume. Starts at 0, ends at pi over 2, because the strip is moving along the y-axis from 0, pi over 2. It's moving up and down, or just, you know, I shouldn't say up and down. Either you can visualize it as going up or down. So my integral is correct. However, I have x in it. The integral is in terms of y, but I have x in it, and x is not a constant. What should we do? I'm going back to the question for a reason. So my integral is in terms of x and y. X is not a constant. If I'm going to integrate with respect to y, I need y here. But unfortunately, I have x. What to do? Any thoughts? Since I know y equals sine inverse of x, take sine on both sides. Sine y would equal sine of sine inverse of x. I'm doing this for you so that you understand things better. So here comes my squiggly, as I call it. Sine inverse would get cancelled. I end up having sine y equals x. Well, I can take that expression, put it in here, pi sine y, square that entire term. So my volume integral would be pi comes out, 0 to pi over 2, sine squared x dy. How do we integrate this? Let's see if you paid attention to class last time. We've got to use a trigonometric identity. Very good, Megan. So we know sine squared u is 1 minus cosine 2u divided by 2. Instead of u, I've got y. Doesn't matter. I could still write the integral 0 to pi over 2, 1 minus cosine 2y divided by 2 du. Do note that I'm not doing u substitution. I'm rather using a trigonometric identity. Okay, so I've got my integral fully in terms of y. 2 is a constant, pull that out. I can't split the integral because I have two terms and they are in addition, subtraction, whatever. So I can write it as integral 0 to pi over 2 dy minus integral 0 to pi over 2 cosine 2y dy pi over 2 integral dy is y. What is the integral of cosine 2y? If you paid attention, not last lecture, lecture before that, I gave you a tip or a trick. And I even suggested that you put this in your cheat sheet or put that in your cheat sheet. Do we remember? What is integral cosine ax plus b? Very good answer. So that's what we need to use in this case. A is 2, b is 0. So the answer is simply sine 2y divided by 2. So I believe it was Lorenzo at the end of class, he asked me, well, am I doing something wrong? Can I just use u substitution? You absolutely can use u substitution. Oops. U substitution here, I'm just trying to save you time. I simply gave you the formula for that. But how do we come to the answer that Carter just wrote or typed? Well, U substitution. Plug in the upper limit, I get pi over 2. Plug in pi over 2 in the second term, you'll end up getting sine pi, and then divide by 2. Sine pi is 0, so that goes away. Plug in the lower limit, no matter which term you plug in, both of them are 0. So the answer is pi squared divided by 4. When we were talking about area between curves, the way I explained, the way I started, is by saying, well, you've been doing area between curves the entire time you learned integrals. You just did not realize it because one of the curves has been the x-axis. So when you find the area under the curve, say y equals x, the top curve is y equals x, the bottom curve is the x-axis, and x-axis is nothing but the function y equals 0. What am I rambling about? This. Y equals x, and top function, bottom function, and pretty much you've been doing, if I call that as f of x and that as g of x, The area under the curve is simply the integral of f of x minus g of x. And that is what the section on area between curves was. Generalizing what you've been doing the entire time in Calculus 1. Okay, if that holds true, whatever we've been doing thus far is a special case of this. Do you agree? In other words, you have been doing volumes using area between curves. Yes or no? You can certainly go back and look at the video on this. I think it is y equals x squared. I'm not sure about the limits. The first problem I did when we were discussing volumes, my question is, what have we been doing on volumes, this method? We pretty much have been spinning the area enclosed between two curves this entire time. Do you agree? Even here, the first problem, I did find the volume using this method of an area that is enclosed between two curves. Yes or no? Yes. Joe, can't elaborate as to what the first curve is up there and what the second curve is? There are two curves. We have an enclosed area. My question is, what are the two curves? Gotcha. Does anyone else want to help out Joe here? Damn it. Okay. Bryce, you are looking at it in a different way. You are looking at it when we revolve it about the x-axis, but Joe has it right. The second curve is x is equal to 0. So that is the enclosed area that I integrated to find the volume. So one curve is x equals 0. What is the other curve? It is not y equals sine inverse of x. Hint, what did we use? Very good. X equals sine of y. So pretty much we have been using area enclosed by two curves to integrate and find a volume. With me? So the disk method, you have a circular disk, but what is it? Well, what are we spinning about an axis to get that circular disk and eventually get volume? Well, area enclosed between two curves. Here is a scenario, slightly modified. Let me answer this. Also, our first problem in volumes y equals x squared. It is a parabola. 0, that point is 1, 1. The strip, in this case, if I'm going to revolve around or about the x-axis, should it be horizontal or should it be vertical? The strip. Very good, Jaden. It has to be vertical. Boom. Great. And we revolved it about the x-axis. Well, someone asked you, well, where is the enclosed area? The enclosed area is right here. What are the two curves enclosing the area? Y equals 0, very good. And the other one, very good, y equals x squared. So the entire time we have been spinning the area enclosed by two curves. So what we did thus far, we called it the disk method because we had disks, we stacked them to find the volume. Again, think of my Wonder Bread example. Now I'm going to have washer method. By all means, disk method is a simple case of washer method. If you know the washer method, disk method is the same. A special case. Now I'll show you how later, but I want you to understand washer method first. So in simple terms, what is a washer? I'm not talking about laundry. I'm talking about, automobile repair, home repair, etc. What is a washer? I'm sure you all put together furniture. You should know what a washer, like a donut. Very good. So by all means, a washer, oops, has a hole in it. This method, we generated a solid. It's got a volume in it. You can, if you're having a cup, then you can fill it with something. But cup, cone, my waffle cone example, if you're using this method, you're not going to get a hollow middle because there is no hole. You'll get a full solid. And that's why I even use the that ice cream form of cone, I forget. But if you want a hole, you would want to spin something in such a way you have a hole for starters. You need to start with a hole. So I have two circles and hole in the middle. Think of donut if you don't want to think of a washer. The inner circle has a radius of its own. Let's call it inner radius. The outer circle has its own radius, outer radius. So inner radius, outer radius. Does the inner circle have an area? If so, what is the area of the inner circle? Only this, it is pi r squared, only this time pi r in squared, inner radius. Okay, what is the area of the outer circle? It's the same logic. We just went from in to out. Very good. Pi r out squared. Okay, great. If I asked you, well, I've got an inner circle, I've got an outer circle. If I had only one circle with thickness, damn it. Okay, it's my weird diff that I tried to draw, could have done a better job, but if I have that diff, there are no holes, and I ask you to find the thickness using the area. Well, a small disk is like a cylinder, so you have area multiplied by thickness. Agreed? So that would be a height. Think of a cylinder that you squish, to a really, really thin disk. So the height becomes thickness, and we know the area is pi r squared. So a disk, no hole, that's what I have. Using the same logic, if I asked you what is the area between the two circles, how do you find that area? In other words, outer circle, inner circle, I'd like to know that. What is the area there in green? Very good. Outer circle area minus inner circle area. So I can write it as outer area minus inner area. That would be pi r out squared minus pi r in squared. Good. Now think of a cylinder with a hole. Well, I started moments ago by saying, oh, here is a cylinder without a hole, squished. I end up getting area, pi r squared, multiplied by thickness, how far you squish that cylinder, have a really tiny height of delta x. This time, I've got myself a cylinder with a hole, and I ask you, what is the volume of a cylinder with a hole in the middle and thickness delta x? What is the answer? Volume of cylinder with a hole Oh, this is doable. Okay, okay looking cylinder. So got a cylinder. There is a hole in the middle. So hole in the middle, hole in the middle. So that hole goes throughout. I want to know the volume. Jaden says the area between the two circles multiplied by the thickness. Very good. So I can simply write it as pi outer radius squared, pi inner radius squared, multiplied by thickness. If I take this washer case, I have a formula, and let's say you are revolving something with an outer radius, inner radius, defined by functions. So suppose I have a line, and then I have some sort of a curve, and I have a point of intersection. So that, oops. That is the enclosed area. I am going to spin it about the x-axis. But when I spin it, I have an inner radius. I have an outer, oops, maybe I should use a different color. Outer radius. What is the enclosed area? Inner minus outer. Sorry, the formula that I wrote, pi r squared out minus pi r squared in. I'm integrating to find the volume. So if you wrote the volume integral here, you would write it as integral pi r out squared minus pi r in squared multiplied by dx. Do you agree? When we were discussing area between the curves, I said, well, as long as you determine which curve is on top of which one, the area would always be positive. So if you get confused, you can always put an absolute value sign. So I could put an absolute value sign just for this explanation. But later, as long as you figure out which is the outer and which is the inner, when you subtract it, you will always get a positive volume. For now, I'm going to put an absolute value sign. So this case, pi r out squared minus pi r in squared dx. An example for that using functions is right here. Now, to do something weird. Let's see if it will let me. Okay, it did. You've got yourself an area. Is there a hole, as in, you know, like I defined, donut hole? Is there one? the top one's got a hole, and we had outer radius, R out, inner radius, R in. I showed you an example of the function. The volume integral is right in the middle. Now I got rid of the inner circle. Let's put that absolute value sign for the sake of it. So how would the integral change? So if you get rid of the inner circle, well, if the circle's gone, its radius is gone. So I end up getting simply pi r out squared dx. Okay, and one more case. This time I get rid of the outer circle. So there is no hole. What would the formula be? Very good. It'll be pi r in squared dx. Okay, great. Look at those two formulas. You've got only one radius. I distinguished them as out and in so I can compare the three cases. But for now, I just want you to look at this integral and that integral. Don't they look exactly like the integral that we've been setting up with this method? Yes or no? Exactly. So earlier, when I first started this, I said this method is simply a special case of Washer method. So I started with the Washer approach. It just became the disk approach when I simply get rid of the hole. So if you thoroughly understand Washer, you can simply use the Washer method always and just realize, well, one of the curves is the axis, then you don't have a hole. You are simply dealing with the disk method. So naturally, if you want a volume for a Washer type of solid of revolution, then you need two curves. Unless you have two curves, such as this one, you won't have an enclosed area, a proper enclosed area with inner and outer radius. So you may ask, well, where is the hole? Well, the hole in my illustration here was right there. So what is going to cause the hole when you spin? This is easy to draw. I am going to dotted line, and the curve looks like a fish. So the one I'm doing in teal is just for reference. So if I'm spinning, so out inner will match up with inner, outer will match up with outer. Same over here, inner with inner, outer with outer. And there is a solid there, but in the middle, there is a hole. There is a gap. So as you move that strip along, the hole remains in the middle. So if you want to get a solid using Gaussian method, you need two curves, and the whole is defined or it's attained by the gap that is in the middle when you revolve about an axis. Are we clear? Yes.